So while we do have our basics axioms 0, 1, and 2, there's nothing wrong with changing that up and seeing what happens. So now I'm going to build a few geometries that use a different set of axioms. The first one I'm going to look at is the 7-point geometry. And for this, there are 3 properties that we need. The first thing we need is we want there to exist 7 points and 6 lines, hence the 7-point geometry. The next thing we want is we want every line to contain exactly 3 points. Before, we needed a line to contain a minimum of 2 points. Now we want it to be exactly 3. And the final one, if 2 lines intersect, they should do so at exactly 1 point. So if they intersect, they should only intersect at 1 point. They can't intersect at more than 1 point. And we want to come up with a geometrically faithful model for this geometry. And that can be really, really tricky if you don't know what you're looking for, because there's a lot of things going on here. So here's the geometrically faithful model for the 7-point geometry. We have a total of 7 points and 6 lines. Every line passes through 3 points exactly, and any 2 lines only intersect at a single point. However, this isn't a great thing because it doesn't satisfy axiom 2. So we can see, for instance, there's no line between E and F. And we can actually solve this issue by adding 1 more line so that we have 7 points and 7 lines, by drawing this line that passes through D, E, and F. And this modified version is known as Fano's geometry. And it's a very special geometry because it's actually what's called a projective plane. So a projective plane is a geometry that adds a little bit more information than just our first axioms. The first thing that we need is there exist at least 3 non-collinear points. So we need to be able to find 3 points that do not have a line between them. Postulate 2 says that every line contains at least 3 points. So before we needed that every line contained at least 2. For projective planes, we need at least 3. Postulate 3, each 2 points belong to exactly 1 line. This means if 2 lines intersect, they can only do so at 1 point. I can't have a line that passes through ABC and another line that passes through ABD, since those would intersect at 2 points. And then finally, postulate 4, each 2 lines intersect in exactly 1 point, so every single pair of lines has to intersect. And if you satisfy all 4 of these, then you would be a projective plane. And the smallest possible projective plane that exists is Fano's geometry, that 7.7 line geometry that we did. Our standard Euclidean geometry is not a projective plane. In particular, it doesn't satisfy postulate 4 because we do have parallel lines, so not every 2 lines intersect in exactly 1 point. So in order to be a projective plane, we have to get rid of the idea of parallel lines. Let's look at a few other different models. The next thing I want to look at is the star geometry. And for that, we're going to need 4 conditions satisfied. The first thing we need 12 points and 6 lines for our star geometry. The second thing, each line needs to contain exactly 4 points. We're also going to say that each point lies on exactly 2 lines. So for every point, we can only have 2 lines passing through it. And then if 2 lines intersect, they do so in only 1 point. So they can't intersect in more than 1 point. And we want to find a geometrically faithful model for this system and then try to determine if it's a projective plane. So we know we need 12 points and 6 lines, and we can see that this is called star geometry. So it's probably going to be a star with 6 lines. So let's start there. So here's a star that contains 6 lines, and if I put points on all of these, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've satisfied the first thing. The second one, every line contains exactly 4 points. You can double check that that is satisfied here, as well as the fact that each point has 2 lines, and that each 2 lines intersect, they do so in only 1 point. So this is a geometrically faithful model for this system. Our next question was, is this a projective plane? So the first thing that we needed is at least 3 non-collinear points, and if you pick any 3 of the points on this star, you can see there's not a line that passes through all three of them. So postulate 1 is satisfied. Postulate 2, every line contains at least 3 distinct points. We can see that every line contains 4 points, so that would work. Postulate 3, each 2 points belongs to exactly 1 line. And this is where we're not going to satisfy. Not every 2 points belong to exactly 1 line. As an example, this point here and this point here, there's no line between them. So this would not be a projective plane. Next, we're going to look at the square geometry. And once again, we're going to have 4 conditions. The first of these is that there are 9 points and 9 lines. We want every line to contain exactly 3 points. We have that every point lies on exactly 3 lines. And then finally, if 2 lines intersect, they do so in only 1 point. So the fact that this is called the square geometry says we probably want to start with a square. We know there are 9 points, so we can arrange 9 points in a square. And the intuitive way to start might be to actually draw the square grid. So that gives us 6 of our lines, each one containing exactly 3 points. We can then go diagonal from the top left to the bottom right. So there's a 7th line. It might be intuitive to now start with the top right down to the bottom left, but then our center point would have more than 3 lines, so that's not going to work. Instead, what we're going to do is we're going to draw a line that starts at this center top point, goes down, and then from there, we're going to come back around the bottom to here. So that would be a single line. And we'll do another thing for the bottom left square. We'll go up, and then we'll keep going around to this top point. And that does give us 9 points, 9 lines. Every line has 3 points, every point has 3 lines, and no line intersects more than once. The next thing I want to do here is try to find some parallel lines. And let's start with some easy ones. One of the biggest notions in Euclidean geometry is that if a line intersects one of 2 parallel lines, it has to intersect the other. And we want to know if that's true in this square geometry. But we can actually see it's not. This line right here intersects my top line but not the bottom one. So just because you intersect one parallel line does not mean you intersect the other. So that's something that we have in Euclidean geometry that's no longer satisfied in this square geometry. We're going to look at one more example known as affine geometry. And for that, we'll need 4 conditions. The first thing, there needs to be at least 3 non-collinear points, so I should be able to find 3 points that do not lie on a line. I want every line to contain at least 2 points. I want each 2 points to belong to exactly 1 line. Finally, given a line and a point not on the line, there's exactly 1 line containing that point that does not intersect the given line. So essentially what that means is if I have a line and another point, I should be able to draw only 1 parallel line passing through that point. So there are lots of different affine geometries. I specifically want to look for one that has 9 points and 3 points on each line. So with 9 points, we might want to go ahead and think of that square geometry again, and that would be a good place to start. So here's the square geometry that we had before. So this is not going to satisfy mainly because, for instance, this point right here and this point right here do not have a line between them, which does violate my condition for an affine geometry. So I'm going to satisfy this by adding in some other lines. In particular, I'm going to add all of the diagonals in the opposite directions. And when I do that, I now have an affine geometry.